Hello, good morning to everybody and welcome to this second plenary talk of the morning. It's a big pleasure for me to introduce the lecture of Xavier Cabré. Xavier was born in Barcelona. He got his PhD in '94 in New York under the supervision of Louis Nirenberg. After that, he held postdoctoral positions in Princeton and in Paris. And while he was in Paris, I remember very well that period, he defended his habilitation in '98. After that, he went to Austin, Texas, where he held the position at the University of Austin. And he was there from 2001 to 2003. And in 2003, he took the decision to come back to Europe. And since then, since 2003, he's ICREA research professor. And since 2008, he's also full professor at the Polytechnic University of Catalonia in Barcelona. Xavier is fellow of the American Mathematical Society, inaugural class of 2012. And he was already invited speaker in a European Congress in 2000 in Barcelona. Xavier works mainly in the analysis of nonlinear elliptic PDEs, and today he's going to explain to us how stable solutions to semilinear elliptic equations are smooth up to dimension 9. Xavier, the floor is yours.
Thank you very much, Maria, for the nice introduction. Let me start saying that it's a big pleasure to be here. Would have been much nicer to be in Slovenia, but anyhow, it is very nice. And let me thank the scientific committee for this great opportunity. It's a big honor. So let me share the screen, the slides. So this is the title: Stable solutions to semilinear elliptic equations are smooth up to dimension 9. So it is a sentence with a verb, right? So you have already the statement, say, of the main theorem. And this is, so I'm going to pretty much present a very recent work. And of course, I will tell you the story behind this, which is more or less 45 years old. In total, for me, it's about 25 years of history of the problem. And the final resolution is what I will tell you today. It's a joint work with Alessio Figali, Xavier Rosoton, and Joaquim Serra, okay? And it already appeared in 2020. So we completed the work in 2019, as you can see in archive. So let's go to the problem, all right? And it is concerned with an elliptic partial differential equation. These equations are called reaction diffusion equations or semilinear elliptic PDE. And it reads as follows: minus Laplacian of u equals a nonlinear function of u, f of u. And this will be posed in a bounded, smooth, bounded domain of Rn, all right? And here, the function u, which is defined in omega or omega bar, the closure of omega, you may think of it as, for instance, a temperature. In our models, it's good to think at u as a temperature. And Laplacian models diffusion, the mixture of heat, say, and F is what we call a reaction term, right? So there is like a chemically active, for instance, there will be later on a chemically active mixture of gases, for instance, or a combustible, and this reacts, and this term has to be understood as a reaction term, for instance, in combustion, right? Going back to the math, say, this equation is the Euler-Lagrange equation of a functional, right? That in classical mechanics, it's called action. And in PVs, we call it energy, but should be called action, in fact. And the functional, it is an integral in omega of two terms. The one associated to the Laplacian is what we call the Dirichlet energy. And it's the derivatives of u squared, and then you integrate. And the other term, there is a minus here, and it is what we call potential energy. And it's the integral of a nonlinear function, capital F of u, where the capital F is a primitive of small f, the reaction nonlinearity. So small f is the reaction nonlinearity, capital F is the reaction potential. Say that later you integrate. Okay, so this whole story is say now we should think that this story now is connected to one of Hilbert's famous problems, the 19th problem, that asks for the regularity of minimizers of elliptic functionals like this one, or there are of other types, more general class of functionals. This is a particular one. So this is a classical problem that it was a main source of development for PDE theory already in the 19th century, 20th century, are minimizers of these functionals smooth, say analytic. Hilbert asked for analyticity. And of course, if there is no reaction term and you just have Dirichlet energy, minimizers, I'm not being totally precise here what is a minimizer, we'll come to this point in a second. Minimizers or critical points even of the Dirichlet energy functional are harmonic functions. And we know that harmonic functions are analytic. So, so that is one of that was what was known. And Hilbert's problem was trying to extend this to more general elliptic integrands here. This is one of them. So an important thing when you talk about minimizers, an important information is going to come from the second variation of the functional. So the first variation of this functional is the equation, right? It's written here. It's the Euler-Lagrange equation. But if you have a minimizer, the second variation, at a minimum, the second variation is going to be non-negative, right? So, so you just compute now the second variation of this of the functional, which is the same as the first variation of the first variation. So this is the first variation. You make one more variation, and what you get, this is a linear term. So you just get an operator which is minus Laplace, and then bring the f to the other side and differentiate simply, and you get a new operator that we will call the linearized operator at the function u or at the solution u for our equation. And it's an operator which is a second order operator, right? And it has two terms. The first one is the second order derivatives given by the Laplace minus the Laplacian, and the other term is a zeroth order term. So if you give me a function v now, I'm going to compute the operator acting on v is going to be minus Laplace of v minus f prime of u times v. All right. So the second order term, first order term. And being non-negative, it gives information because minus Laplace, if you think of Fourier or integrating by parts, minus Laplace, it's a positive operator. And instead here we have a minus, and as you will see in a second, I will be thinking of nonlinearities f for which f prime is positive. So with the minus, this is negative, and minus Laplace is positive. So these two guys are competing, right? And the sign is not clear of this operator in principle. But if you are at a minimum, the second variation is non-negative, and you have this additional information. This is the non-negativeness of this operator, turns out to be the same as a quadratic form associated to this symmetric, it's a symmetric operator being non-negative. And the quadratic form, when you evaluate this on a function v and you multiply by v again and integrate, or let me call it psi to like in my slides, the non-negativeness is the same as this quadratic form being non-negative, or bringing to the left-hand side the zero-order term. It's equivalent to this relation here. So this is the information we get from being a minimizer or a local minimizer, second variation non-negative. And it says that given any function psi, this is what we will call test function. It's arbitrary, as smooth as you need, and vanishing on the boundary of omega, or with compact support. This C here means compact support, but vanishing on the boundary would be enough by density. And you have this information that f prime of u, that, as I told you, we will be thinking mainly in our head that it's a positive function, times psi square when integrated is less than the Dirichlet energy of psi, okay? And all right, so in our hands we will have this information and the equation, two main ingredients, say pretty much these ingredients. And in fact, now a definition comes in the title of my slide, stable solution. So this is in fact the definition of stability. I will say that a solution of the reaction diffusion equation is stable if and only if the second variation of energy is non-negative definite, which is the same as this. And therefore, when you have a stable solution, it's a more general class than minimizers, than absolute minimizers, or even than local minimizers or minimizer under a small perturbation. It's a little more general, but I would be happy to already, if my result, I could prove it for local minimizers. Local minimizers meaning minimizers for small perturbations, or some people call relative. I don't like relative. Local minimizers is the correct word. But we can even consider this larger class, which are stable solutions. All right. Okay. So this is just like general calculus and differentials of functionals posed in this particular case of this type of energy or functional, which is Dirichlet minus potential. All right, good. So several remarks. First, the test function psi vanishes on the boundary of omega. Therefore, when I'm playing this game of seeing who has less energy, which is like a game, right? Who wins? The competitors in this game, they all have the same boundary values as the function u. So note that I didn't prescribe any boundary values in the equation. And therefore, but u will have its own boundary values. And then the game that I'm playing is among people who have the same boundary values as you. All right. And I'm saying that u is a local minimizer, or at least a stable solution. So this is the same as what happens in a classical problem that I will mention several times during my exposition, which is the problem of soap bubbles or minimal surfaces. Think of R3. You have a wire, right? You have a given wire, a Jordan curve in R3. And then you look at the soap film spanned by the bubble. There can be one, or there could be more than one. We will come back to this later. But the game is to see which film has less area among all the films that have the same boundary values that are spanned by the same wire. Right, so this is the correct setting in classical mechanics and in this geometric problem of minimal surfaces, or in this problem that we will see that it's like a combustion model. All right, another comment. I already mentioned a little of this, but let's be more specific. in our mind and the interest in this problem and the difficult case about the Hilbert question is to focus on nonlinearities which are first non-negative, so reactive and not absorbing heat, say reactive, non-negative and more than linear, superlinear at infinity. That is, when temperatures will be large, the Laplace of U is a linear function of the temperature, right? It's linear. Instead here, I will be thinking of a nonlinearity which is superlinear for U large, for large temperatures, like U squared would be an example of superlinear, right? U squared. And then an important thing to notice is that in this case, no absolute minimizer exists of the functional, all right? In Hilbert's question, in fact, the class of functionals that he wrote and that were first attacked in the literature, in general, admitted absolute minimizers. But in this case, there will be no absolute minimizer. Why? Well, if you take your favorite function, any function, say positive function, let's think of positive things, and you scale it, you will just multiply it by a constant t. Look how the energy looks like. The first term, the Dirichlet energy, is quadratic in t, and then the potential energy will depend on t, and the t will be here. And since small f is more than linear, capital F is more than quadratic. So this will grow faster than t squared for t large. And therefore, this energy, of course, as a function of t, just one real variable, goes to minus infinity when t is very large and there is no absolute minimizer of the energy, right? So now it looked that it could be like that the Hilbert problem has no meaning for this energy, but that's not the case. There are no absolute minimizers, but there will be stable solutions. So now, after these comments, the question is: are there stable solutions or local minimizers of the energy or not? And yes, the answer is yes, of course. And a good way to see it is from a model in combustion proposed by Frank and Kamenetski in 1969, and then retaken by Barenblatt and Gelfand in some years later, 1963. And the model that I will describe in a second, let me start more focusing on the model, is the same equation as before, but adding a parameter lambda, positive parameter lambda, in front of the reaction term to make it smaller if lambda is small, or larger, stronger if lambda is large, okay? And now I will fix zero boundary values, okay, to clarify my mind. Zero temperature on the boundary of the container omega, all right? And I will be thinking of positive solutions because F will be positive, lambda will be positive, U will be super harmonic function, which is zero on the boundary, is positive. And in the model, there is no problem to think that F is positive even at zero. It is non-decreasing, it is convex, and it is superlinear at plus infinity. And these are the model nonlinearities that you should have in mind and that were first considered in this problem. The exponential nonlinearity, which is in fact the one that was first considered in relation with this combustion model, because it comes from the Arrhenius law in chemical kinetics. Or you could think of the powers, but not the pure power, u to the p, because you will see that now this plays this condition f of 0 positive plays a role. So we will add a constant 1 plus u to the power p bigger than 1, okay? So in fact, f of 0 being positive makes that 0 is not a solution of this problem. Well, forget about what I wrote here, u positive. I think of U non-negative, U equals 0 is not a solution. It satisfies the boundary value, but the Laplace of 0 is 0, and instead f of 0 is not 0. So it's positive, and lambda will be positive also. So 0 is not a solution. So in principle, the problem has no trivial solution, right? So you ask yourself, does it have solutions or not? And this is not difficult to see, and this is from the 70s or even the 60s, that there is a parameter lambda star that we call the extremal parameter, which is positive and finite, such that for every lambda less than lambda star, there is a positive solution. And in fact, it is regular, C infinity. If f is C infinity, it will be C infinity and analytic. If f is analytic, it is bounded, so totally classical means like regular, smooth, okay? It is stable, that is that we care about this fact, okay? And it is a monotone family as lambda increases. So as lambda gets larger, U lambda gets larger. And as lambda tends to the extremal parameter, U lambda converges to a function, U star, that we will call U star. And we will call it the extremal solution of the Gelfand problem. And it is an L1 function, that's easy to see. And it is a weak or distributional solution of the problem for the extremal parameter, which is also stable. Stability passes really well by monotone convergence, Levy theorem, in the limit as lambda tends to lambda star, all right? But it is, I'm saying that it's only L1. This solution, in principle, that will be our problem to decide if it is classical, bounded, or not, all right? Okay, I said that we call it the extremal solution of the problem. And then later, for lambda greater than lambda star, there are no solutions. For instance, first, it was known that there are, and this is easy, there are no classical solutions, almost by definition of lambda star. For the moment, that. So let me just say a word what it means this physically in combustion, okay? The real problem in combustion you need to add a term, the heat operator instead of the Laplace operator. So you consider the nonlinear heat equation ut minus Laplace u equals lambda f of u. You put 0 temperature on the boundary and you give an initial distribution of heat in your body, this initial distribution. And then this is a model for self-ignition. Self-ignition means like if a certain reactive mixture of gases, for instance, that there will be in the container, will go through self-ignition or combustion or not. And the answer is that for lambda less than lambda star, self-ignition fails. And the container remains for a long time. It converges to a temperature, which is this U lambda. It is a stationary distribution of temperature that corresponds to the long time behavior of the temperature of the container, say. And it is classical and finite, therefore finite temperatures, and here self-ignition failed. Instead, for lambda larger than lambda star, there is a success for the self-ignition or combustion. Okay, I will not say more on this, but just to get an idea. So some years later, 72, right? So 63 for Barenblatt and Gelfand. Then 72. There was a seminal paper by Joseph and Landgren studying the radial case. So suppose the container is a ball in Rn, okay, the unit ball. And let's start with they started with the model nonlinearities. Let's focus on the first one, the exponential one. They, through ODE techniques, phase plane analysis, because in the radial case, the PDE, the Laplacian, reduces to an ODE, of course. Through phase plane analysis and ODE theory, they could see the following fact, that Up to dimension 9, let's forget about dimension 2. Let's say up to dimension 9, the family of stable solutions, which is this branch here that we know that increases as lambda goes to lambda star, converge to the extremal solution and this extremal solution turns out to be bounded. So classical also. Besides, they saw then by the implicit function theorem that this branch cannot die here. It turns back, okay? And there are other solutions of the problem for other parameters of the reaction parameters lambda. But all these other solutions are not stable, are unstable, right? Are not stable. So in principle, you won't see them in real life, or it will be much more difficult to see them in real life. Okay, stable solutions, in fact, are those that in general you can see in real life. We'll come back to this with minimal surfaces in a second. Instead, in dimension 10 and higher, the extremal solution is unbounded. All right. Okay, I need now to accelerate a little. And in fact, people, probably them, I'm not sure if they were the first, realized that there is a explicit singular solution in all dimensions, which is pretty much the logarithm of the distance to the origin. We are still in the unit ball. It is a nice function with finite energy. This W12, it means that it has finite energy. So I will call it's an energy solution of this equation. This is a very simple computation with the ODE. This is a radially symmetric function. You compute the Laplacian and you get that it's a solution of the Gelfand problem for this parameter. And it is singular, right? Because at the origin, it blows up. Exactly as it happened in dimension 10 and higher, what they could prove, Joseph and Andren. So now, once you have this explicit singular solution, what you should do is to look at its stability. Is it stable or not? Because we are caring about stable solutions, right? So you do the linearized operator, which is minus Laplace minus 2 times n minus 2, the derivative of the exponential is the exponential, and the exponential of this function is 1 over x squared. And it is very simple to see if this second order operator is stable or not, because it rescales perfectly well. Both terms rescale the same, and therefore Hardy's inequality tells you it's going to be stable if this parameter here, 2 times n minus 2, is smaller or equal than what we call the Hardy constant, the best constant for this operator to be non-negative, which is n minus 2 squared over 4. You do the algebra here and you get n greater or equal than 10. So this explicit singular solution is stable in dimension 10 and higher. And therefore, using this, then one can prove that in fact the U star here that we knew it was unbounded, it is exactly this function, but in dimensions 10 and higher, not in smaller dimensions, because the U star is a stable solution, and this singular solution is only stable in high dimensions, right? Okay. Similar things can be done for powers. So the natural question is, all this was in the unit ball first, and second, for the exponential nonlinearity. You could ask yourself what happens in general domains and for general nonlinearities. When is the extremal solution bounded? When it is not? When are energy stable solutions bounded? In general, stable solutions of the equation in the first slide, and not only the extremal solution, if I forget about this parameter lambda. So these are the questions. And the first thing to say is that if you don't care about the stable solutions and you care at a larger class of all solutions, stable or not stable, L infinity estimates are tough, are tough and are expensive to have, to get, all right? And in general, L infinity estimates can only be proved for some nonlinearities f. Which ones? Those nonlinearities that we call critical or subcritical, all right? And this means that the nonlinearity grows at most as a power of the temperature of U, as a power with, for certain powers, power speed smaller or equal than this exponent, which is connected to the Sobolev exponent in the Sobolev embedding. In this case, when the reaction term is not so big, say the exponent is not too big, it is possible to use the equation and prove that any energy solution at the end will be bounded, okay? It's like an extension of linear results, say, but for a nonlinear problem, using that the exponent is not too large and using the equation and the Sobolev inequality, right? Otherwise, if f, for instance, the exponential nonlinearity, of course, does not satisfy this, and you, in general, you don't have an infinity estimate for general solutions. So now we restrict to stable solutions, right? And we have an idea of what happens in the unit ball, at least for the exponential nonlinearity. And for the powers, it happens the same. This dimension 9 and 10 is also the cutting edge, say, the cutting dimension for the powers, say. All right. So now the problem is set, right? And I should tell you that it is a PDE, a reaction diffusion PDE analog of a very famous problem in differential geometry, which is the regularity of stable minimal surfaces in a ramp. So I go back to soap films, and I could consider those soap films which are minimizers of the area, absolute minimizers, if they exist, or a general class, a larger class, sorry, which are stable minimal surfaces. And you can ask if they are regular or if they can have singular points, like conic points or points where there is no tangent plane to the soap film. And what is known is that the regularity does not hold in dimensions 8 and higher. And in fact, in dimension 8, there is an analog object to this one, which is an explicit singular stable minimal surface, which is called the Simon's cone and has a very simple equation. Like this is simple equation. So then you take this Simon's cone and you see that it is stable in dimension 8 and higher, right? But not in low dimensions, like in our case. So in low dimensions, you would expect regularity. But surprisingly, say, this is only known to be true up to in dimension 3 for two-dimensional surfaces in R3. And this was proved in the late 70s, 80s independently by Fischer, Cabré, and Shang, and by Do Carmo and Penn. So the problem is open in dimension 4, from 4 to 7, and this is a very important problem and very difficult problem. By the way, for absolute minimizers, so absolute minimizing, what we call minimizing minimal surfaces, the regularity is known up to the optimal dimension 7. So changing the class of minimizers by this larger class of stable solutions is a tough thing in general. In minimal surfaces, for instance, it's very tough, all right? Okay. So let me now start the story of what was known and about this problem. Okay, I'll have to accelerate a little. After Joseph and Landren, 2 years later, Crandall and Rabinovich proved something very nice. The extremal solution is bounded, and therefore, once it is bounded, using the equation, you can prove that it is infinity if the nonlinearity f is infinity. It is bounded in every bounded smooth domain omega up to the optimal dimension 9. If the nonlinearity in any container, if the nonlinearity f and its first derivative and second derivative behave very much very close to the exponential. So this means f very close to the exponential, f prime very close to the exponential, and f second very close to the exponential. So it's a quite very restrictive assumption on f, on the nonlinearity. Or as a power, same result with if f behaves like a power, and derivative of f and second derivative of f as the first derivative of this and second derivative of this. But okay, this result is very nice because it holds in any container, any geometry, and tells you, okay, it looks like 9 is the right dimension for the regularity of the extremal solution. And the argument, in fact, is not so important to use that you are dealing with the extremal solution, but it applies to every energy stable solution of a reaction diffusion equation, independently that you put this parameter lambda or not, okay? So, but here for convenience, I stated for U star, okay? So this is 75, and then 20 years later, when I was in Paris, as Maria said, I was a postdoc in Paris 6, working within the group of Jaime Bresis and Henri Berestiki, but it was Jaime Bresis who produced a revival of this problem after 20 years, Bresis and his group, all right? And in fact, what they did is to study the Gelfand problem, adding the time dependent, so the real time dependent problem. And they prove a nice theorem about this extremal parameter lambda start and how self-ignition produces for the time dependent problem. And it is pretty much through blow up of the temperature in finite time, but I'm not going to enter in details. The thing is that that was a very nice work of Bresis and collaborators, and we all got very excited, say, about this this problem. Again, the time dependent and the one that I'm telling you about, the elliptic one without time, and then there were several papers related to the problem, and one of them, for instance, was Jaime with Juan Luis Vázquez, and there is a list of open problems, and one of them says, is it, by the way, is it always the extremal solution in the energy space, in the Sobolev space? But let's focus more on the second one that is also written, and in another paper of Jaime by himself. By the way, I have to thank Jaime for his vision on the importance of this problem and that it could carry nice mathematics behind, as you will see that is the case. He wrote something like almost literally, he almost wrote literally, is there something sacred about dimension 10? In the meaning, perhaps we can prove the same result for all nonlinearities in all containers. Or not, perhaps not. Is it possible to construct a singular stable solution in low dimensions for some domain and some nonlinearity? So I have to say that at that point, we had no clear idea, even precise, if the answer was yes or not. What was the correct answer, okay? So let me tell you the story a little quick. Grégoire Nedev proved the result, the conjecture in the positive. When I say the conjecture, I mean in the positive way, regularity up to dimension 3, and Nedev was a student of Jaime Bresis. I will not read the rest. I have to accelerate a little. 5 years later, I proved with Antonio Capella, a student of me at that time, that the stable solutions are bounded and therefore regular up to the optimal dimension in the radial case for every nonlinearity. So this is a nice result. It's still in the radial case, but it's a nice result that gave the idea, and at least convinced myself, that the result should be true, or could be true, okay, in general domains, because here we could accomplish all possible nonlinearities F, no restriction at all on it. Every stable energy solution is bounded, all right. So I'm thinking about this. I've been thinking about this problem. I'm working on this problem since '95 when I was in Paris. This is 25 years ago. And the main developments made by me were, well, besides the one of NetDepth, the main developments are these ones, the one of 2005, and then in 2010, I could pretty much extend the result up to dimension 4, all right? So still there were the dimensions 5, 6, 7, 8, 9. These are 5 dimensions left, all right? In 2000, there were other developments, some tries, like in 2 years, some years later, with Xavier Rosoton, also with Joel Sprague, but they were partial results in terms that we had to assume quite a lot on the geometry of the domain or in the type of nonlinearity. But by 2013, I had a good idea that almost solved the problem. And I got a computation that pretty much proved that the stable solutions would be up to dimension 9, and for every nonlinearity turn out to be what we call BMO, functions of bounded mean oscillation. This, I will not enter in details. Many of you know what is BMO. If not, just think that this result means that the solution is not bounded, but almost. For instance, it is in LP for in LQ for every exponent Q. It's in all the Lebesgue spaces for every exponent Q, LQ. And this, so by 2013, I knew this, and in every domain and for every nonlinearity. So the result was almost there, but going from BMO to L infinity turned out to be very difficult. And from 2013 to 2019, these 6 years where I spoke, I told my computation and to several people, around 5 or 6 people, say selected people by me because I didn't publish this result. And there was no way to get the L infinity estimate. After several visits to Zurich, where at that time there were Alessio Figali, Xavier Rosoton, and Joachim Serra were all there, and we could prove the result. So couple of visits. And the result says like this is the main theorem. Okay, I start with a smooth solution, a C2 solution. The important thing will be the estimate, okay? Once we have the estimates, then I will be able to prove regularity for weak solutions, energy solutions. So take a C2 stable solution of an equation in the unit ball of Rn. Now I work in the unit ball, and but it is not a radial solution. Huh? The boundary values, I don't know what they are. It's not radial, not necessarily radial. And the only thing you have to assume on the nonlinearity is that it is non-negative. Then, in every dimension, in the interior, half the ball, the gradient of U is in L2 and even a little more. 2 plus gamma, with gamma positive, depending only on the dimension n. And the estimate is beautiful and linear. On the right-hand side, there is only a very weak norm of the solution, the L1 norm, probably almost the weakest you can imagine in this context. And the relation is linear. It looks like it's linear on U. The nonlinear problem, the nonlinear part of the problem disappeared here in this estimate. It's linear, and this is thanks to a stability. It's like if stability allows you to fall, like in a linear theory, right? Like in the book of Gilbert Rutger, say. And this holds in every dimension and solves one of the open problems posed by Brezis and Basket. And then up to dimension 9. The solution is bounded, and not only bounded, it's Holder continuous in the interior with a beautiful linear estimate, also with a universal constant that all depends on n, only depends on n. So it is an open problem to know if the non-negativeness of F is needed or not, right? Up to dimension 4, we know that it is not needed, but from dimension 5 to 9, it is an open problem. So now I will really accelerate, right? And let me tell you, the second main theorem is what about regularity up to the boundary? And we can get it. We need the domain to be C3, but we need more assumptions on the nonlinearity, non-negativeness of f, non-negativeness of the first derivative and of the second derivative of f. So f increasing or non-decreasing and convex. And in this case, you put 0 boundary values, same equation, and you have also a W1, 2, even a little more beautiful estimate up to the boundary in all dimensions, and up to dimension 9, a Holder, beautiful Holder estimate up to the boundary, and in particular, an L infinity estimate. All right, so let me say that for the P Laplacian, a very recent work of me with Pietro Miraglio, Manuel Sanchon establishes the optimal result when P is bigger than 2, and regularity holds also for certain dimensions, small dimensions, and this is optimal for P bigger than 2. And the optimal result for P less than 2, it is still open. And for the fractional Laplacian, which is very much under study by many people today and nowadays, the optimal dimensions are open. A result up to the optimal dimensions is open, even in the radial case, okay? I have to skip this extra information and just, I have 5 minutes to describe a little the proofs, okay? The proofs start from the stability inequality, and then you take a test function, you write the test function and the product as the product of 2. One that will vanish on the boundary and will be less important, and the most important thing will be the first choice of this function C here, all right? When you write the stability inequality for a product of 2 functions, C times eta, and you just integrate by parts, it's very easy to see that it becomes this expression here, where on the right-hand side, you have C squared, and on the left-hand side, you see the linearized operator acting on C. This is very important. So you need to choose a function, an appropriate function C, satisfying some type of, well, satisfying some nice equation related to the linearized operator, which is what is behind the stability. All right. So in my radial case, this choice, this starting point was motivated also by minimal surfaces, where Simons did the same trick and took C, the curvature of the minimal surface, the curvature, the length of the second fundamental form. Back to our problem, and this is again the starting point, is what you have at your disposal, and you have to take an appropriate test function. In the papers of Trandal, Rabinovich, and Nedev, this trick, bringing this function C, was not used, and the stability inequality was used in the first form, in the primitive form, with Xi, and the test function that was chosen was a nonlinear function of U, choosing H appropriately, depending on F. Instead, in the radial work and in my work up to dimension 4, the two crucial test functions C appeared, which are different. In the first one, it was the radial derivative of the function U. In the radial case, it was quite natural to try for UR or RUR, doesn't matter, which is the same as X grad U, all right, in general. Instead, in the work up to dimension 4, not radial, but in general domains, the test function that I took was the modulus of the gradient. Okay, let me tell you that for our result in the paper with Figali, Rosotone, and Serra, we need to use both at the end. Okay, we need to use both. You compute the linearized operator on both, and you insert this here. All right. It's not easy, it's not difficult to compute this, and then you insert here, and then you try to manipulate, and you still have at your disposal the choice of the function eta. That will be, as in minimal surfaces, will be a power, this will be the eta, a negative power, like the Green's function or the fundamental solution, say, but another one, the square root, in fact, a negative power of the distance to the origin. And you simply compute in the stability inequality after you chose x grad u as function c and eta this power, you compute, you get 3 terms pretty much. You choose the right power not to spoil everything. And not to spoil everything, you have to take this power and you compute, you make some algebra. And what you get is something like this. You get an integral, and I will finish in 2 minutes, Maria. You get an integral of not the Dirichlet energy, but the radial derivative of u squared, radial with respect to a point. But then later I could choose the point wherever I want, because I'm in a general domain, say, times the Newtonian potential, say, x to the power 2 minus n, and the 3 terms combine together and give an algebra, which is this one, surprisingly. And this was the computation I did in 2013, n minus 2 times 10 minus n. So you will get information only up to the optimal dimension 9. So the computation brings in or brings up the right dimension 9. And what you get in the right-hand side is something computed in the annulus. And it is the same, but instead of having the radial derivative, you have something in principle larger, which is the grad u square. And this was the difficulty that took 6 years to replace here the grad u square by the radial derivative to have on the left and on the right the same object, but integrated in the ball on the left-hand side and on an annulus on the right. And then you should believe me that once you have the same object on both sides and on the right, it is only integrated in an annulus, then a very well-known linear trick in PV theory, Hall filling, brings you to decay in rho for this quantity that brings you to Holder regularity, because this is a scale invariant. Look, this is quantity is a scale invariant. dx, the Lebesgue measure, has a dimension n, which gives this minus n. Here you have a 2, and derivative to the power 2, it's a minus 2. So it's scale invariant, like the L infinity norm. So this quantity rescales like the L infinity, and if you get decay, you overpass L infinity and you go to Holder continuity. So the difficult part of our paper was how to replace the gradient u square by the radial derivative square. And I will not be able to tell you this. Maybe if somebody asks in the questions, I can tell you the main idea. So thanks a lot for your attention.
Thank you very much, Xavier, for this very beautiful talk. It's very nice to see that after so many years you have managed to solve this problem that you really wanted to solve so much. Okay, so I see that there are 2 questions for you. The first one is by Maxim Siskin. He asks about, you made the assumption that F was non-decreasing. What if otherwise? Is it not interesting to look at the other case when F is not decreasing?
No, it is of interest. And for the interior problem, for the interior result, sorry, we don't need F increasing. So for theorem 1, all what we need is F non-negative, which means that U is superharmonic. So here we can include decreasing nonlinearities or not monotone nonlinearities. Instead, for the boundary regularity, we need non-decreasing and convex. And it is an open problem to know. But the answer is, I would say that all nonlinearities are, for me, are of interest. Even if F changes sign, what can you prove theorem 1?
Okay, thank you. There is another question by Hardy Chan. He thanks you for the talk, and he asked, in the fractional case, where does your key fail to work? Only the product role, or is it there is something else?
Can you repeat, Maria, in the fractional case?
In the fractional case, where does your key, function key, or I don't know, key, fail to work?
Okay.
Is just only the product role, or is there something more? The test function.
Yeah. Well, let me say that in the fractional case, we would get we are trying to do, and it should work at the end, is the same to take as test function this function here, x times the gradient of u, and then a power, and for eta a negative power, to 2s minus n over 2. It's simply the computations, Hardy, the computations that you have to do, like the Pogozaev trick. You have to do Pogozaev, but now involving also an extra ingredient, which is a negative power of x. And we don't know how to integrate by parts and do the Pogozaev trick in the right way. We don't know, neither using the extension for the fractional Laplacian, neither working downstairs, how to get the right algebra. But let me tell you, since we have some time, that to get the optimal dimensions, so you could ask, how do you know the optimal dimensions? Okay, the optimal dimensions, I know them by first, because there is an explicit solution, which is the logarithm. The logarithm also solves the fractional Gelfand problem. And when you look at its stability through the fractional Harding equality, it gives you what we believe that should be the optimal dimensions. And this is a complicated relation saying that n has to be less or equal than something, but it involves gamma, several products, and several gamma functions. So hypergeometric functions of n and s, and combinations of n and s. So the relation is complicated, but we know it. And then there is a very nice result by Xavier Rosoton, which says the optimal result has been obtained by Xavier Rosoton for the exponential nonlinearity in not only in the radial case, but in convex symmetric domains. This is a beautiful paper from his PhD. So we know that we really expect that these optimal dimensions this relation gives the optimal dimensions, and we know it at least in one case for the exponential nonlinearity.